Welcome back, Algebra 2 students. We're in Lesson 33, and we're going to review the major rules of algebra. So the first rule says the same quantity can be added or subtracted to both sides of an equation without changing the solution of an equation. And we know that's true. We can test that theory out by saying x plus 2 equals 4. And when we subtract 2 from both sides, we get x is equal to 2. And when we take this value and plug it into our original equation, we get 2 plus 2 equals 4 because 2 is the value of x. We know that's a true statement. So we know we have not changed the value of the solution by making these equal changes to both sides. If you will, you think about a scale, like a balancing scale that would have a little dish here. And to keep it balanced, you have to have the same weight here that you have here. And as long as the weight stays the same on both sides, this would remain perfectly straight up and down, which would indicate that it was balanced. And these would stay level, which is another indicator of it being balanced. So having the same on both sides, or doing the same thing to both sides, if I changed this weight over here to 5, I would have to change this weight over here to 5 to keep it balanced. If I wanted to take 2 weights off, I'd have to take 2 weights off over here. And that is the idea and the governing principle of whatever you do to one side, you have to do to the other, because we have that real life illustration that shows us that that is what's going to maintain the balance. And maintaining the balance helps us find the solution that gives us the right answer. If we don't maintain that balance, then these two things are no longer equal. So we have to do that. We have to remember the concept of the scales being in balance, and whatever you do to one side, you have to do to the other side in order to get the right solution and to maintain the equilibrium of the equation. All right, that was the rule number 1. Rule number 2, so rule number 1 is the balance the scales. Always balance the scales. Do the same thing to each side. Rule number 2 is that every term on both sides can be multiplied or divided by the same quantity without changing the solution to the equation. And that's illustrated when we have something like x over 3 equals 5. What we're doing is we're saying that we can do the inverse operation to both sides and maintain the equilibrium. It's the same thing as the scales we're looking at over here. If we divide here and we undo that, so we multiply everything times 3, this cancels out because when you multiply and divide a number by the same number, they cancel each other out. That's like saying 3 times 2 divided by 3. Well, that's 6 divided by 3. The answer is 2. So we just did the reciprocal, or not the reciprocal, but the inverse operation. And that means that we didn't do anything at all. So when we do that, we just bring the original number into play. We show it for what it is. And if we take this value of x and we put it back into the equation, 15 over 3 equals 5, we can see that it is indeed a true statement. 15 divided by 3 is 5. So the inverse operation works. It also works for division. If I had 2x equals 6, I could divide both sides by 2 because the inverse operation of multiplying these two factors is division. And divide 6 by 2, x would equal 3. Right? So if I put it back into the same original equation, 2 times 3 does indeed equal 6. So we know that that is a true statement and that it proves the ability to use the inverse operation in order to solve for x. But it also proves the rule that as long as we multiply or divide both sides by the same operation and the same quantity, then we will get the same answer. We will get the true answer. And we'll keep the equation in equilibrium. We'll keep it balanced if we do the same thing to both sides. So that's really what the first two rules are all about. It's just that whatever you do to one side, you have to do to the other side, or we put the equation out of balance and it is no longer a true statement. And mathematics, if it is anything, it is the pursuit of truth in our number system. We want to know what is true, what makes this equation true. We can't do that if we don't maintain an equilibrium or a balance. All right, so our third rule is all about numerators and denominators. It's talking about fractions. Let me clear the page. And it just says that the denominator or the numerator of an expression can be multiplied or divided by the same quantity, non-zero, without changing the value. Only the form of the expression is changed. And we see that's true when we have a fraction like 1/2. And let's say we need to add that to 2/8, right? We cannot add these without a common denominator. We know that. So we multiply this by 4, the top and the bottom. So we end up with 4/8 plus 2/8. That's a math problem we can do. We can actually add that and get 6/8. Does the value of 1/2 change? No. 4 is half of 8. So this remains the value of half. It's just in a different format. A format that we can actually perform a calculation with this other fraction. And the same is true here. We could take this 6/8 and we can divide it by 2, the top and the bottom, and we end up with 3/4. Does it change the value of 6/8 to say that it's 3/4? No, because 6 is 3/4 of 8. It's not the whole thing. It is 3 out of every 4 units, and that is all this is saying. So we can multiply to find a common denominator so that we can perform math, and then we can divide in order to reduce, to simplify a fraction. And that's all this is saying, is that if we do that, we have to multiply the top and the bottom number, the numerator and the denominator, by the same number to keep it the same value. And we have to divide by the same number in order for it to keep the same value. That's all rule number 3 says. So we agree and understand how that works, and we agree that it does work. We agree that is the correct way to treat equations and the correct way to treat fractions to maintain the truth in our statements, in our mathematical expressions. So let's look at something that's a little bit more complicated. Let's say we have a problem that is using more expressions with variables than with real numbers that we can actually understand and evaluate. So because we understand how to do that to numbers that we can actually evaluate, we can apply the same rules to these fractions with variables that we can't evaluate. All we can do is rearrange them in a way that we know follows the rules and makes sense. So what we're going to do here is find a common denominator so that we can add 4 and py together and get one answer. And the way to do that is to just multiply these two denominators together, and that gives us x times x plus y. That's really as far as we need to go. And the reason we don't want to go ahead and multiply those and get x squared plus xy is because we might be able to factor something out. We don't know that yet. And until we know that, we want to keep it in as simple a form as possible for the sake of future possible reduction, because we don't want to have to multiply it out and then factor it again back down in order to reduce it. So we leave it like this to save ourselves some steps on the back end. So now we multiply 4 by what we added to this side to get the common denominator, and that was x. So 4x. And the same thing over here for py. We have x times x plus y. So that would give us that x plus y is the new part. So we multiply py times x plus y. And now that they are both on the same common denominator, we can add them together and put them into one expression, one fraction. But because they don't have any common terms, this is 4x by itself, the variable x alone, and py times x would be pyx. That wouldn't match, so we just leave it as pyx. And this wouldn't match, so that would be py squared. We don't have to multiply it out, but I did just to show you that we have no like terms that we can combine. So we would leave the expression like this. That would be as far as we could take it. And we don't have to multiply this out if we don't want to. We see that there are no x's in all three. Well, there's an x here and an x here, but there's not an x in the third term. So we can't factor anything, which we were kind of hoping we might be able to do. But we can't, so we leave it like it is. There's no point in taking it to the next step because we know it's not going to simplify anything. Right? So this will be the answer to the above problem here. Excuse me, I'm fighting a little bit of a cold. Trying to get over it. So let's apply this to a couple of our example problems. Let me clear the page and we're going to do example 33.1 and 33.2. So 33.1, let me pause. I'm going to pause on my side. You won't see it, and I'm going to write these up here. All right, so here are our two problems. Now, there are a couple of different ways that you can solve this, but the easiest way is keep it, change it, flip it, and I stand by that. So when you have these two here, two fractions that are divided by a third, or vice versa, I find that it is easier to go ahead and find a common denominator and turn this into a single fraction. That's my preference. It's not something you have to do. So I'm going to show you what happens when you don't do that. So we have two fractions and we have this fraction on the bottom. We're going to keep it, change it, flip it, and turn it into a fraction distribution problem. So when we flip this, we change the sign, we flip this, what we end up with is y over a, because we flipped this, times x over y plus 4 over yx. And I'm writing my y's with a tail because I'm trying to not confuse myself because there's a 4 in this problem. And my y's sometimes end up looking like 4s. So I'm making myself do the little curl on the y to tell the difference. Just in case you're wondering why I'm doing that. And so then we just distribute. You know, I don't know how much simpler to make this than to do it like this. You could do the common denominator first and then just have two fractions. It's up to you. It doesn't matter. You can do it whichever way you want. I did it this way just to save that step on the front end, and we might do it on the end. So yx over ay plus 4 times y, and then ayx, right? Because ayx. All right, so now we have these two, and we need to find a common denominator, and the difference between the two is x. So all we have to do is multiply this fraction times the x. We end up with x squared y plus 4y all over ayx. Easy peasy. That one was not hard at all. All right. Now, there is one thing that I just noticed that we can do, and I'm wondering if you guys notice it as well. We can take y out of both of these and factor out the y, because we have a y here and a y here and a y here. And when we factor something out of the bottom, we have to be able to take it out of each term in the top, because the whole thing is one value. Now we could have easily done that up here and made it a little bit simpler. We could have taken the y out here and the y out here, and then we would just multiplied it by the x. But it doesn't, you don't have to do that. You're going to factor it out eventually. It would probably have been easier to multiply had we done it sooner, but it's just as easy to take it out here. You just have to remember to take it out of each term once you get to the bottom. So our answer is going to end up being x squared plus 4 over ax, because we were able to factor the y out of each term. So think about that. Before we got to this step, you could have seen that. I could have seen that. Sometimes I have to refer to the book to see everything there is to see. But again, keep track. The hardest part of these types of problems is keeping track of all the variables and how they move around. So give your work a once over. Look for the common factors in the tops and the bottoms. That's going to be what you need to look for. All right, let's do 33.2. And we just learned something here. We learned something about ourselves. If you caught that while I was doing the problem and you chose to factor it out before I did, good for you. I learned that I need to make sure that I check for that next time. So as you do a problem, grow from each experience. And remember to do your steps that make you better. So I'm going to do this in the same way I did this one, just because it works, and it works well. So I'm going to say a plus m over x times a over x plus y plus m over y. And then I'm going to multiply a times a plus m. Remember, if you don't want to go ahead and do a squared plus ma, to write it with the parenthesis, that reminds you that this has to be distributed to both of those, okay? Same thing for x times x plus y plus m times, and I just put the single in front because that makes the most sense when you write it out. You can write it behind. It doesn't change the value. And then this would just be xy, right? All right, now because we're on this step right here, and I remembered that I could have factored something out, I'm looking for that now. I don't see anything here that I can factor here, and I don't see anything here I can factor here. So I'm just going to go ahead and multiply. I'm going to find a common denominator, and that's going to be xy times x plus y. All right, so now I just need to multiply this right here by y. So it's going to be a y times a plus m plus, and then I need to multiply this side times x plus y. So that's going to be m times a plus m times x plus y. And that's my final answer, because there's nothing that I can take out of all of these expressions. You can't factor out the y here without factoring out a y here, and there's not a standalone y that you can factor. You can't factor out the x here because you can't take it out of here. You can't take it out of an expression without also taking it out of this expression. So there's nothing we can factor, so this is our final answer for 33.2. So always check, see what you can factor when you finish. If you can't factor anything out, let me circle this as our last answer, then you know you're done. And that is all we really had for lesson 33. It was just mainly a review of how to deal with a little bit more complex problems and more complex fractions, and just to go over the rules to get you to this point where you can see how to work them and work you into more difficult things. All right, so I will see you in lesson 34.